As scientists, one of the most important things that we can and should be thinking about is how much confidence we have in measurements we make in the laboratory. Each instrument we use will report out a certain number, and that number absolutely comes with some sort of a corresponding error. The point of this video is to think about that error and where it comes from. And let's approach this using a very generic idea, right? So if we are thinking about a target, right? So we have our target here, which has a bullseye, okay? So ideally, if we were to shoot arrows at this target 15 times, all 15 times would hit within our bullseye, right? And in this case, we would have a lot of confidence in each of the measurements we make. Every time we shoot that arrow, we know it's going to hit the bullseye. And in this case, this measurement would have a high degree of accuracy and a high degree of precision. Okay, and if a measurement has a high degree of accuracy and a high degree of precision, then we're very, very confident in making a single measurement that we're going to get the right number. Okay, so accuracy refers to the correctness of that value. So how close is this measurement to the actual value? Precision refers to how reproducible is this number. So in this first example, we see that these 15 measurements all hit in roughly the same spot, and it's the correct spot, it's the bullseye. So that's really accurate. And they're also really precise because every single one of the arrows hit in about the same spot. So it's very reproducible as well. Let's consider a second situation. So we're looking at the same bullseye here. Okay, we're looking at the same target. And in this case, as we shoot the target, we see that our arrow is not hitting in the same spot every time. However, if we were to average these measurements, what we'd see is since they're surrounding the target, right? So since they're surrounding the bullseye, if we were to average them, we would get the correct number. So this measurement actually has a reasonably high degree of accuracy. So it would be considered reasonably accurate. However, since these measurements do not lie on top of each other, since we don't see reproducibility, this is a very poor precision. So we have a very poor degree of precision. Let's consider a third situation. So in our third situation here, we're looking at exactly the same target. So we have our target with a bullseye. And in this case, as we shoot the target, we do see that all of the shots, all of the arrows, hit in roughly the same spot. So since this measurement is very reproducible, we are precise, so we have a high degree of precision. However, since these are not at the bullseye, it's not accurate. So we are not getting the correct measurement, so we are not accurate. But since each of the shots hit in the same spot, we do have a high degree of precision. Okay, and then our fourth example would be the same target again. And here we're going to look at what it might look like if we have a poor degree of precision and a poor degree of accuracy. So if we were to make these shots and they were all to line up towards the left side of this target, if we were to average these, they would not average to the target. They wouldn't average to the bullseye. So this measurement is not accurate. We also see that we don't have very good reproducibility. Each shot is landing at a different spot. So this is also not precise. So this instrument, this measurement, is not accurate and not precise. Okay, so why does this matter? Well, these ideas of accuracy and precision are built into the idea of error. Every single measurement we make has an error associated with it. We have a certain level of confidence in that number. Okay, so let's take, for example, a scale, right? So if we have a scale here and we have somebody stepping onto this scale, that's a person, right? So this scale that they step onto is going to report out their weight or their, let's say, their mass. Okay, so this scale that they're stepping onto has its measurability limits. So it has a limit to how confident we are in the mass that it reports. Okay, let's consider a couple of different masses that we register. Let's consider a mass of 0.1502. We could also report out 15.02. We could also report out 15. Okay, so 3 different scales, each of these scales reporting out a different number. So the way that accuracy relates to these numbers is the total number of significant digits is a report of accuracy. Okay, so the total number of sig figs is a report of how accurate the measurement is. So in this case, we have 4 sig figs. In the second example here, we also have 4 sig figs. So these 2 measurements would be considered to have equal level of accuracy. But this third measurement only has 2 sig figs, so it's not as accurate of a measurement. Okay, so accuracy relates to the total number of significant figures that are reported. The precision relates to the total number of decimal places. So the more decimal places we have, the more precise the instrument is. So in this case, I have 4 decimal places, and in this measurement here, I only have 2 decimal places. So this measurement is more precise than the second measurement. The second measurement only reports 2 decimal places, so it's not as precise. So these 2 measurements have equal accuracy but different precisions. This measurement, the third measurement, does not have any decimal places, so it's not as accurate or as precise as the first 2 measurements. So punchline, accuracy determines how correct a value is, how correct a measurement is. And when we're thinking about that in terms of measurements of numbers, of actual physical values, that's reflected in the total number of significant figures in the value we report. The precision is how reproducible that value is, and that's determined by the total number of decimal places that are reported.